Right triangle trigonometry applications. Before we start looking at problems, we're going to need to remember 3 facts about right triangles to solve our applications. The first is we have to remember that the angles of any triangle sum to 180 degrees. We have to remember the Pythagorean theorem, which of course says that a leg of a right triangle squared plus the other leg of a right triangle squared equals the hypotenuse squared. And we have to know our SOHCAHTOA relationship. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Here's a little bit more vocabulary that we're going to need to be familiar with. The idea of angles of elevation and depression. The angle of elevation and angle of depression are always from a horizontal line of sight. So let's assume we have this horizontal line here. The angle of elevation goes up from that horizontal line, so it's like I'm looking upward at something. If I'm talking about an angle of depression, here's my horizontal line, and I'm looking down at something from the horizontal looking down. So to kind of help with that concept, thinking about from a person's standpoint, let's assume that the horizontal line we're referring to is their line of sight where they can see. So this horizontal line here, we'd say their angle of elevation towards, let's say, looking at an object is given by this angle here going up from the horizontal line of sight. And then the angle of depression, again, is from that horizontal line of sight looking down at maybe some other object. So maybe what might help understand this is the word depress or depression in angle of depression. Like if you're looking straight ahead, if you're depressed, maybe you're going to look downward from the horizontal line of sight. Let's move on and look at some examples. The first ones will be a little bit easier because they'll come with a picture or a diagram, and then we're going to have to build a diagram going into future problems. So here we're told the length of the shadow of a building, 34.09 meters tall, is 37.62 meters. So let's pause right there. We're told the length of the shadow of a building, 34.09 meters tall, so the building itself, as you can see from the corresponding diagram, is 34.09 meters, and the length of the shadow is 37.62 meters. So the way this picture's been drawn here, well, if here's the sun, the shadow is going to be on this side of the building. So if the sun is on the left side, the shadow is going to be on the right-hand side. And we're told that shadow length is 37.62 meters. Find the elevation of the sun, round to the hundredths place. So the elevation of the sun, we're looking for the angle of elevation, would be from the horizontal line of sight. So in this case, that's going to be the ground level. So we're looking for this angle of elevation here, B, and in terms of the angle B, we have its opposite side, so directly opposite angle B, I have the side length, 34.09 meters, and then I also have the adjacent side to angle B, which is 37.62 meters. So I have opposite over adjacent in a right triangle, so we're going to have a building, which we're going to, of course, assume that it's perfectly straight up and down so that this forms our right triangle. So we want to find the measure of angle B. We have its opposite side and its adjacent side, so the trig function that we're going to use is tangent. Tangent of an angle is opposite over hypotenuse. So we're going to set up tangent of angle B, that's what we've been given here, that it's called. Tangent of B is opposite 34.09 over adjacent 37.62. And we're in search of the value of B, we're in search of the angle. And this isn't something that we can just look at and identify because of the decimal values, right? This isn't a nice value, so we don't know exactly what angle to plug into tangent to get out this value. So we are going to turn to using our calculator here because in order to get the value of B, we have to do tangent inverse. So to get the value of the angle, we need the inverse trig function. So the value of B is equal to tangent inverse of 34.09 over 37.62. So this right here is my exact answer. This is my exact answer. But I was asked to approximate it or round to the hundredths place. And this is where our calculator comes in. So here we want to make sure that we are in the correct mode. So we do want to write our answers in degrees on these problems. So we'll go ahead and, I'll go ahead and provide the value here. And I encourage you to check on your own scientific calculator. The value here from degree mode of tangent inverse of this quotient is going to be approximately 42.18 degrees. And I stopped 2 places past the decimal because that's the hundredths place. So we have to know our place values. This is tenths, the first position after the decimal, then hundredths. So 42.18, and then I'm in degree mode on my calculator, so 42.18 degrees is my angle of elevation of the sun. Moving on to our next example. A lighthouse, which is 18 feet high, stands on a cliff that is 150 feet above sea level. So here again, we have an easier setup because we have the corresponding diagram. We have a cliff 150 feet tall, and the lighthouse, which is 18 feet high, is on top of that cliff. We're being asked, or also given, the distance from the top of the lighthouse to a sailboat on the ocean is 360 feet. The distance from the top of the lighthouse, that's over here, to a sailboat on the ocean is 360 feet. So that distance from the top of the lighthouse to the sailboat is 360 feet. What is the angle of elevation? So now here's what we're being asked, right? We have a question. What is the angle of elevation from the sailboat to the top of the lighthouse? And this time we're going to round to the nearest whole number. All right, so here we are in search of this angle of elevation. So from the horizontal line of sight of the sailboat up, right? Angle of elevation from horizontal is going to go upward. And we have the opposite side of this angle x, so directly opposite this angle x, right? We have opposite. And then this time we have opposite over the hypotenuse. So we can see this right triangle forming. It's right triangle applications. So here we have over hypotenuse, right? So we have opposite over, that's supposed to be a little arrow, got kind of ugly there. So this opposite side over this hypotenuse. So the trig function that we're thinking about is sine. Sine is opposite over hypotenuse. We don't have any information about the distance from the sailboat to the base of the cliff, right? We just have the distance from the top of the lighthouse to the sailboat. So that's the hypotenuse. So we're going to set up that sine of x this time. So in my diagram, I have x as the angle. Sine of x is opposite. Well, opposite is this total height here, which is 168 feet, if I add these two together. So 168 over hypotenuse, 360. And again, we're in search of the angle that you plug into sine to get out this value, which we don't know offhand, right? We do need a calculator for that. So we're going to need to find the angle, which is sine inverse of 168 over 360. So again, this is my exact answer, but I'm asked to approximate by rounding to the nearest whole number. So in a calculator, this is approximately 28 degrees. So again, I'm in degree mode on my calculator when doing sine inverse here. So this is my approximate value. All right, in this example, we are given this information. From the top of a 210-foot cliff, Paul observes a lighthouse that is 430 feet offshore. So from the top of a 200-foot cliff, now this problem is different. We don't have a diagram. So if we don't have a diagram, we need to construct a diagram. So we're going to go ahead and remember that we don't have to be artists. Our diagram is going to form a right triangle here. So we're going to just go ahead and draw our 250-foot cliff as just a vertical straight line and say that that measures 210 feet. So we're thinking about from the top of this cliff, Paul observes a lighthouse that is 430 feet offshore. Well, where's the shoreline? The shoreline would be on the bottom of the cliff, right? That's where the water is going to be. So down here, just for your reference, right, this is going to be the shoreline down here. So my lighthouse is 430 feet offshore. So from the bottom of my cliff, again, this vertical line is the cliff, my boat is going to be 430 feet off the shoreline. So I'm going to go ahead and draw another line, this time a horizontal line, and say this is 430 feet away. That's where the lighthouse is. So I will go ahead and maybe try to construct like a little lighthouse situation. Again, we don't have to like be artists here. So we have our 430 feet offshore here. So we can see we've created a right angle. Now the question itself is, find the angle of depression from the top of the cliff. Remember, this vertical line is our cliff. From the top of the cliff to the base of the lighthouse, round to the nearest whole number. Find the angle of depression. So this is also different from the problems we've done. Those have both talked about angles of elevation. Alright, so the angle of depression is always from the horizontal line of sight. So we're saying Paul's up here at the top of the cliff, so we're talking about from the horizontal line of sight, the angle of depression to the bottom of the lighthouse, the base of the lighthouse. So the angle that we're actually looking for here is this one. I'm going to go ahead and call it theta. So find the angle of depression from the top of the cliff to the base of the lighthouse. So we think the horizontal line of sight going down. I cannot tell you how many mistakes I get that students put this angle right here as the angle of depression when it's not. The angle of depression is from a horizontal line of sight. Alright, so here we're looking for this angle theta. And then we're going to round our answer to the nearest whole number. Alright, so here, one of the issues that we have is that the angle that we're looking for is not inside of our obvious triangles. We have this right triangle here, and we have the two side lengths, the two legs of the right triangle. But then we have this theta that's on the outside. So what we can do, though, is we can think about extending the horizontal line, that perfectly horizontal line right there, that leads us right up to the lighthouse, and recognize, well, if I stop right at the base of the lighthouse, that's also 430 feet. And then if I head straight down, that's also 210 feet. So basically, I do have this right triangle outside here. So if I now have this right triangle, I'm looking for this angle theta. I have its opposite side, right? So directly across here, that's its opposite side. And then I have its adjacent side, right? 430 feet. So I have opposite over adjacent to work with. I'm trying to find theta. So we're going to go ahead and use the trig function tangent. Tangent theta is equal to opposite 210 over adjacent 430. And so we can go ahead and cancel out the zeros, right? And then if we're in search of theta, we have to do tan inverse. If we're in search of the angle, we do the inverse trig function, tan inverse of 21 over 43. And in a calculator, that is the approximate value to the nearest whole number of 26 degrees. So again, this is my exact answer, but plugging it into my calculator is going to give me an approximate answer because it does keep going in terms of digits. Right? But we're going to round to the nearest whole number. So this is one way of doing it, of thinking about just that there is this other sort of right triangle on the outside. The other thing that you can recognize from your geometry is that because these lines are parallel, so here we have these two lines are parallel, they're perfectly horizontal, the shoreline and then the horizontal line of sight, and these two horizontal lines are cut by what we call a transversal. So when two parallel lines, these horizontal lines are parallel, are cut by a transversal, opposite interior angles are congruent. So that means that this angle here, down here by the base of the lighthouse, is also theta. So if I have parallel lines cut by a transversal, then opposite interior angles are congruent. So we could have thought about instead, okay, well, theta is inside the original right triangle, and we have its opposite side and its adjacent side, so that's why we were using tangent. So two different ways of thinking about finding that angle theta. In this next example, we have a light attached to the top of a building is shining down with an angle of depression of 30 degrees on a man that is standing 16 feet from the base of a building. So a light attached to the top of a building is shining down with an angle of depression of 30 degrees on a man that is standing 16 feet from the base of the building. So we're going to go ahead and start by just drawing the building. All right, so let's go ahead and draw our building, and we have a light attached to the top of the building. So I'll just kind of draw like a little circle here and kind of just put a little light. That light is shining down with an angle of depression. So remember what that means from the light's horizontal. I'm going to draw a horizontal line here. So from the horizontal line where the light is, the angle of depression, so from that line down, is a measure of 30 degrees. So I'm going to go ahead and kind of draw this line here to indicate that angle of depression. Whoops, didn't need to zoom in like that. So I have this angle right here of depression of 30 degrees, and this light is shining down on a man that's standing 16 feet from the base of the building. So I'm going to go ahead and draw this man here, shining down on the man, and he's standing 16 feet from the base of the building. So we'll go ahead and say this is like 16 feet right here. Now the next part says, he casts a shadow that is X feet long. The man casts a shadow. Well, if the light's over here, right, then the shadow is going to be on this side. So if the light is on the left, then the shadow is going to be on the right side of the man. So the length of the shadow, we're told, is X. Right? The length of the shadow, we're told, is X feet long, so we don't know how long. The distance from the light, so the light is up here on the top of the building, the distance from the light to the tip of his shadow, which would be over here, is 30 feet. So from the light down to the very tip of the shadow, so we're being essentially given the hypotenuse of this right triangle we can see forming. That big, long, giant distance is 30 feet. So I'm going to go ahead and label that. That is 30 feet. Now we're being asked, how tall is the building? So let's go ahead and give that a variable name. We already have X. How about we call it Y? How tall is the building? What is the length of his shadow? Well, that already has a variable name X. This is the shadow. And how tall is the man? So we're being asked multiple questions. Let's go ahead and give that a variable name. Let's say that's H for height of the man. Okay, so we just want to make sure we have everything correct, right? We want to, feel free to double, triple check reading the problem, all the values. So the light is on the top of a building. It's shining down with an angle of depression, right? So from a horizontal line of sight down, shining down on this man that's standing 16 feet away from the base of that building. He casts a shadow that's X feet long, so here's his shadow, and the distance from the light's up here on the top of the building where it said it was, to the very tip of the shadow is 30 feet. And then how tall is the building? How long is the shadow? How tall is the man? Round all answers to the nearest tenth. So here we're being asked for multiple pieces of information. We're given multiple pieces of information. So we want to go ahead and kind of look at what we have, identify our right triangles, and kind of go from there. So I definitely see this right triangle at the base of the building and the floor. So I have essentially this big right triangle right here. Well, I'll just go ahead and use a pen here. So we're talking about this big triangle here. Let's go ahead and focus on that one. But then there is going to be this like smaller triangle that we can take a look at eventually. But let's just think about the bigger one for now. I can kind of see that a little more obviously here. Well, right now I have no other angles in this big triangle. I have this right angle, but I don't have the two interior angles. So what we want to do is either recognize that we have the whole geometry situation from earlier, that two parallel lines, both of these are horizontal, the top and the bottom, cut by a transversal, would give us opposite interior angles. So this angle down here is 30 degrees. Right, so those opposite interior angles, because the two parallel lines cut by this transversal that is the hypotenuse. Or the other way we could figure out the interior angles is to recognize, well, this would be perfectly a right angle up here. And if this is 30 degrees, then this is 60 degrees, right? So 90 is a right angle minus 30. So this piece right here is 60. And then we have 90 and 60. So this down here is going to have to be 30. So we're using all these facts about right triangles or just a right angle. Some have to be 90. So either way, now we have both of the other angles here. So we have the angle 30 degrees. We are interested in finding the opposite side length. So maybe we go for how tall is the building first, even though we can go in any order here. It feels like the easiest route to just recognize I have this angle 30 degrees, I want its opposite side, and I have its hypotenuse. So focusing on the big triangle, I want its opposite side and I have its hypotenuse. So we'll go ahead and start by saying sine of 30 degrees is opposite y over hypotenuse 30 degrees. Now, in case you were wondering, because there's multiple ways to find the values in this problem, so what we could have used was 60 degrees. We could have said, well, I'm going to use 60 degrees and I want the adjacent side, which would be y, over the hypotenuse 30. So we could have done cosine of 60 is y over 30. So both would give us the same value. Now here, sine of 30 degrees, we don't need a calculator for that. That's on the unit circle. We know that's 1/2. So 1/2 is equal to y over 30. Multiply both sides by 30. 1/2 times 30 is 15. So y is equal to 15. Now 15 what? Our units of distance here are going to be in feet. So the height of the building, y, is 15 feet. Right? Or since it's round to the nearest tenth, it's no real rounding, but we can at least put 15.0 feet, because we know it is that accurate. It's exactly 15. So this is the height of the building. This is the height of the building. So now we also have, whoops, height of, that's a funny B, height of building. So now we also have that this is no longer a missing value. So this value right here is 15, and it's not an approximation, it's 15 exactly. So we've answered the first question here. So now what we're interested in finding the remaining parts. So the length of his shadow, how tall is the man? So now, again, we're searching for x and we're searching for h. Well, if I do think about this little triangle right here, I'm fairly limited. So I do have this little triangle inside the bigger one, but I don't quite have as much information. It is a right triangle, but I don't have really anything to kind of work with here other than all the angles. I have 90, 30, and this would of course be 60 because they all add to 180. But I have no side lengths, so I have no idea what the hypotenuse is. Like, I can't just assume that it's like half of this. Some people make that assumption. And I don't have his height, I don't have the base, so I have no side length. So I don't really want to go to the smaller triangle, at least just yet. So I'm going to erase that. So I'm kind of stuck thinking about the bigger triangle still, so we're going to go for x. We're going to go ahead and try to solve for x. So what some students recognize, and it's not wrong, I'm going to go ahead and start to set it up, is that it's a right triangle. We can use the Pythagorean theorem. So I have the hypotenuse, I have the side 15, and I can find this entire side length here, and then just subtract 16 from it. So here's what I wouldn't want to do. I'm going to go ahead and do it in red and then kind of just erase it. So yes, this whole side length here is 16 plus x. So we could set this Pythagorean theorem up. We could say 16 plus x squared plus 15 squared equals 30 squared. So we could do that, but now I'm solving for x, and this is like a mess. I'd have to FOIL this out, like 16 plus x times 16 plus x. I have some pretty big numbers, 15 squared, 30 squared. What I could do is just say, okay, how about I call 16 plus x, let's call it a different variable. I don't know, let's call it s for side. And then replace this with an s instead of 16 plus x squared. And then when we get s, that's the whole thing, we could subtract 16, s squared, sorry about that. So we can do this. I mean, this isn't as bad, so it's still pretty big numbers. So we can go ahead and go this route. So we can say like s squared, so 30 squared, so it's like 900 minus 225, and then take the square root of that. So we're looking at the square root of 675, that's the whole thing, and then we can subtract 16 from it. So we can go ahead and go that route. There is nothing wrong with it, but a lot of what we try to do is just use trig ratios. So what we can do is, let's see, I'm going to go ahead and erase the s part for a second. I'm going to go ahead and try to set up another trig ratio here. So involving this whole side x, so we will say this whole thing is 16 plus x. And I'll stick with just using the 30-degree angle, the one down here, but again, you could use 60 degrees. And I'll say, well, focusing on 30 degrees, I want the adjacent side, and I have the hypotenuse, so we can do this time cosine of 30 degrees equals adjacent, that's 16 plus x, over hypotenuse 30. And then we can go ahead and solve for this value of x. So again, we don't need a calculator for this. Cosine of 30 is radical 3 over 2. And then equals 16 plus x over 30. 30. And we can multiply both sides by 30. And so 30 over 2 would give us 15. So we have 15 rad 3 equals 16 plus x. And then we can go ahead and subtract the 16. So 15 rad 3 minus 16 is equal to x. Now this is the same answer, again, that we could have gotten from doing the Pythagorean theorem. So it's just, this is simplified, 15 rad 3, because we had the square root of whatever it was, 575, or 675. So this is just simplified, but this is the exact answer here for this shadow length. So this shadow length right here exactly is 15 rad 3 minus 16. Now we were told to round all answers to the nearest tenth, so x is approximately, let's see, it's 9.98. So funny enough, that does round to the tenths place to 10.0. So 9.98 is going to round to 10, and this is again in feet. So this right here is the shadow length. And now we have something to work with inside of that smaller triangle. So inside of this smaller triangle, I have one of the sides. So I have an angle, I have 30 degrees. I want its opposite side because that's the height of the man, the last thing left. And I have its adjacent side. So I can go ahead and set up tangent of opposite over adjacent. So tangent of 30 degrees is equal to opposite h over the adjacent side length. Now I don't want to use the approximate value. This wasn't exactly 10, right? There's an approximately symbol here. It's approximately 10. It's really 9.9807 blah blah blah. I never want to use a rounded answer if I can help it. And I can help it here. I can put 15 rad 3 minus 16. And so now, to solve for the value of h, I'm just going to multiply both sides by 15 rad 3 minus 16. So it's going to look kind of ugly, like tangent 30 degrees times this 15 rad 3 minus 16. Right, that's equal to h. So that's my exact answer, but I want the approximate answer for h. So I want to make sure and keep this in parentheses, this difference here, and then multiply it by tangent 30 in my calculator in degree mode. And I end up getting that the height of the man is approximately 5.8 feet. Again, all these distances are in feet. We were not solving for angles, we were solving for side lengths. And we want to make sure that our answers make sense in the context of the problem. So in a problem like this, we have a general number sense, like, yeah, the height of a man could be about 5.8 feet, right? That's a logical height. So we wouldn't want to get out that the height of the man was 15 feet, right? That's not a very logical conclusion. So that's part of the reason why in our application problems, we do want to evaluate or plug these into a calculator and round just to kind of get a general sense of if we're doing our setup correctly. So this was the height of the man, and we have answered all parts of the question. This next problem is going to kick it up in difficulty. So here we have a 300-foot tall radio tower is located X feet from a building. So a 300-foot tall radio tower is located X feet from a building. So what we'll do is we'll go ahead and start to just sketch things out. I'm going to go ahead and sketch my building over here. And then we have that this radio tower, which I'll just go ahead and draw as like a vertical line, let's say. Or maybe just like a little skinnier thing. This is my radio tower, is X feet away from the building. So I have this distance here of X, and the radio tower was 300 feet tall. So this over here was my radio tower. I'm going to go ahead and say that's 300 feet. Now, from a window in the building, so over here this was our building, this was our radio tower. From a window in the building, a person determines that the angle of elevation to the top of the tower is 36 degrees. So I'm going to go ahead and put a little window in the building, and there is an angle of elevation to the top of the tower that is 36 degrees. So I don't want to put my window up here because I made my tower kind of stop a little bit shorter here. So I'm going to go ahead and plant my window just right here and kind of say, okay, here's the little person that's inside of it. And what they're saying is that from their window in the building, the angle of elevation to the top of the tower is 36 degrees. Now remember, it's from that horizontal line of sight. So I'm going to go ahead and attempt to sketch this horizontal line as like a little dotted line there, dash line. So from the horizontal line of sight upward. So angle of elevation goes from the horizontal line of sight up. So this right here, this little angle is 36 degrees. And that the angle of depression, so they also notice from this window, that the angle of depression to the bottom of the tower is 23 degrees. So from this person in the window, going up to the top of the tower is 36 degrees, to the bottom of the tower is 23 degrees. So from this line of sight down, so I'm going to go ahead and draw the angle of depression here, that's 23 degrees. Now because I just went ahead and planted the window anywhere, we can see that this picture is not to scale. So this angle here that I've constructed is actually smaller than this angle down here. But it's okay, we'll just go ahead and leave it. So this is my angle of elevation up, this is my angle of depression down from the horizontal line of sight, right? So this angle right here is not the angle of depression, right? This one is. All right, so now the question is, how far is the tower from the base of the building? So here was the radio tower, here's the building. Essentially, find x, right? Solve for the value of x. Let's go ahead and kind of look at what we have going on here. So sometimes students just kind of look at this and think, okay, well, these two angles, I can add them together and get this entire angle, which sure you can, that's going to be 59 degrees. But this angle here is within this larger triangle, which is not a right triangle, right? This is not a right triangle. So having this angle here doesn't really help me. It also doesn't involve the side length x. So that's not really what I'm going for there. So what I want to do first is recognize that the distance from the base of the building to the base of the tower, x, is also the length of this horizontal line of sight. So this is also a length of x right here. And so what I want to do is actually think about two separate right triangles now. One of them being this one here, so involving that horizontal line and then the angle of elevation. And so this right here is one right triangle. So now at least it does involve one of my angles and then the x that I'm in search of. But then I also have to take into account the other right triangle with the angle of depression of 23 degrees. Whoops, getting a little messy there, sorry about that. Of 23 degrees, and then also with that side length x. But the problem is, I don't have these individual side lengths that lie along the tower side. So what I'm going to go ahead and do is call one of them a variable name. So we don't know, let's say inside of this top triangle, we don't know this side length, so let's go ahead and give it a variable name, right? Let's call it y. So if this little height right here is y, and this whole tower is 300 feet, then that means that the height of this other triangle inside here, the one involving the angle of depression, is going to be 300 minus the value of y. So the whole tower and then minus y. So this is 300 minus y. So now I at least have some representations for the side lengths here, but I had to introduce this extra variable, right? So that's why this one does kick it up a notch in difficulty. So let's go ahead and at least now create our ratios of our trig functions like SOHCAHTOA. Which ones do we have? So if I think about the top triangle, I have the angle 36 degrees. I don't have the opposite side, but I've labeled the opposite side y, and then I have labeled the adjacent side x. So we are talking about tangent. So we'll go ahead and say tangent of 36 degrees is y over x. So I have one relationship, one trig function relationship involving x and y. And then we'll go ahead and set up the trig ratio I have involved for the bottom triangle involving the angle of depression. So in regards to 23 degrees, I want to include the opposite side, 300 minus y, and the adjacent side, x. So we'll go ahead and say tangent of 23 degrees is equal to opposite 300 minus y over x. So what I have here is two different equations, both involving x and y. So I have essentially a system of equations. So what I want to go ahead and do now is solve one of them for an individual variable. So I want to go ahead and, let's say, take this tangent 36 degrees equals y over x and solve it for one variable. So one variable equals, and then the rest of the stuff on the other side. So the easiest thing to do is just multiply on this equation both sides by x. So x tangent 36 degrees is equal to y. And then we're going to use the substitution method to solve this system of equations. So I'm going to go ahead and plug y over here into the other equation, and then that will involve all x's, because remember, what are we trying to solve for? We're trying to solve for x. So we're going to take this value of y and substitute it into the other equation. So we have tangent 23 degrees is equal to 300 minus, and so we're going to go ahead and plug in that x tangent 36 degrees and then over x. And now what we want to do is solve for x. So this equation that we have, it only has x's in it. We have one equation with just x's, so we want to solve for x, get x by itself. So I'm going to go ahead and multiply both sides by x. So I get x tangent of 23 degrees is equal to 300 minus x tangent of 36 degrees. So again, if I multiply by x, that will cancel with this x on the bottom. That's why there's an x over here now. I want to solve for x, and there's two x's, one on the left, one on the right. So I'm going to add the term with an x to the left-hand side. So I have x tangent 23 degrees plus x tangent 36 degrees is equal to 300. And then we're going to factor out the x. So we have an x in common in both. We can go ahead and factor it out. we get x tangent 23 degrees plus tangent 36 degrees, all that's in parentheses, is equal to 300. And again, we're solving for x, so we're going to divide by tangent 23 degrees plus tangent 36 degrees on both sides. So I'm going to go ahead and make some space. So here we have x is 300 all over tangent 23 plus tangent 36 in degrees. So this is my exact answer here. And now I want to approximate it. I've been told to round to the nearest whole number. So when I plug this into my calculator, I just want to make sure and include parentheses around the denominator. So 300 over the quantity, tangent 23 degrees plus tangent 36 degrees. And that's approximately 261 feet. So this one is not an angle, right? This one is not an angle we're solving for. We're solving for a distance. So I was in search of how far is the tower from the building. And the units that we were given here in terms of distance were in feet. So 261 feet. Now, one of the things I want you to recognize is that we waited until the very end to approximate. So we had tangent of 23 degrees, tangent of 36 degrees, and we did not early on plug them into our calculator and work with those approximations, because that's going to lead to a further off value in our final answer if we approximate early. So we don't want to, let's say, plug this tangent 23 degrees into our calculator and use that number, and then plug tangent 36 degrees in up here and use that number, because that's going to lead to more error in our final answer. So we never want to approximate, if we can help it, until we get to the absolute final step and substitute it into our calculator.